This lesson will deal with value returning functions. In the previous lesson, you learned how to create and invoke void functions, which are functions that do not return a value. Creating and invoking a value returning function is very similar to creating and invoking a void function. You typically enter the same three items of information, that is, a function prototype, one or more function calls, and a function definition. The syntax for creating and declaring a value returning function differs from the syntax for creating and declaring a void function in two basic ways. First, a value returning function syntax begins with a return data type, which indicates the type of data the function will return. You will recall that a void function syntax begins with the keyword void, which indicates the function will not return a value. Secondly, the last statement in a value returning function is always return and then an expression, where the expression represents the only value the function will return. A void function does not return a value. Demo 8 will serve as an example for value returning functions. You will note that under the function prototypes, I now have three functions declared. The void is the display line, which was used in the previous example. The two value returning functions are calc square and calc half. This program will behave in the same manner as the previous demonstration. It's just that now this is using value returning functions to do the calculations as opposed to being done in the main function itself. So we have the function prototypes defined. Note that the keyword float is in parentheses to indicate the type of parameter being passed. You'll also note, and this is what makes this a value returning function, is that the keyword float precedes each function prototype. This indicates that the result of this function will return a float data type. Scrolling down to the calling statement, or statements, you'll note that there are two statements that are being used to call these functions. The result of these functions have to have some place to be stored, and they're being stored in number squared and number halved, respectively. The calling statement is actually embedded in the expression. Calc square is the name of the function. Number input is being passed to this function. Number input, you'll recall, is the number which the user inputs. And likewise, calc half is passing to its function also the value of number input. Scrolling to the function definitions, you will note that we now have function headers for both calc square and calc half. Inside of each of these functions, we have a local variable, that is num_sq, which is the local variable version of the num squared. And the calculation takes place here, where we're simply multiplying number input times itself. You'll note that the return statement is returning the value of num square. This num_sq is a local variable, but since it's associated with the return statement, it gets returned to the calling statement, and in turn gets returned back to the value of number squared, which then gets displayed as the result. The same thing takes place with the calc half, where we have a local variable called num_half. The calculation takes place, which is the number input divided by 2, and then the return statement returns the value to the calling statement, which in this case is here. And then the result of that calculation gets stored in number halved, which then in turn gets displayed in the cout statements below. Let's compile this program to observe the execution. If I type in 9, you'll notice that the calculations still behave as you might expect. The square of the number and the half of the number has been calculated. Once again, from the user's perspective, there's really no difference between this version and the version used previously in Demo 7. Demo 8 is a program you might want to study in more length. The Demo 9 program is one that requires some debugging. This program will compile normally, but when executed, it will produce incorrect results. Before compiling the program, let's take a brief look at it. It has a function called calcsum, which is going to accept and process two float variables. The calling function will call the function and pass to it the numeric variables num1 and num2 respectively, which are entered by the user. After the calculation takes place, then cout statements will display the two numbers along with the sum. The function itself is a very simple one, where you simply are adding num1 and num2 and returning the value of that num1 and num2. I'll compile this program. By the way, an alternative to clicking on Build and then Build Demo 9 is to use the shortcut toolbar button that you see here. This, of course, is in Microsoft Visual C. You'll notice that the program does compile normally, and then we'll execute. I'll type in the number 7 and the number 8. And as you can see, the program returns the sum of 7 and 8 is 0, which obviously is the wrong answer. You may want to retrieve this program from your disk. It's called Demo 9, to see if you can determine where the problem is. From a syntax point of view, this program is working perfectly. The problem is that there is no place for the result of this calculation to be returned to. The calling statement is structured correctly, except if we want to display the sum, then we need to tell it that the value of sum is the result of this function. So we should let sum equal the calcsum function, which is num1, num2, being added together. Now let's recompile this program to verify its results. And then re-execute. And I'll enter the number 7 and the number 4. And as you can see, it does perform the addition correctly and displays the result of 7 and 4 as being 11. Once again, you might want to study this program as another example of value returning functions in a program. In all demonstration programs up to this point, we have not been concerned with the number of decimal places that have been displayed in our output. You can specify number of decimal places by using C's stream manipulators, which will format the output so it displays a certain number of decimal places. You are already familiar with one of the C stream manipulators. That's called inline, or ENDL, which advances the cursor to the next line. C has many other stream manipulators. Two examples of these are set precision and set iOS flags, which you can use to format your program's output. Unlike the inline stream manipulator, which is defined in the iostream.h header file, the set precision and set iOS flag stream manipulators are defined in a header file named iomanip.h. So therefore, in order to use these manipulators, we need to include an additional compiler directive, such as include iomanip.h. This will now give us access to the so-called stream manipulators. A stream manipulator is like an on-off switch. You turn it on when you want the compiler to start using it, and it will remain on until you give it a different command or turn it off. I wish to display the result of my calculations here, so I will include another cout statement that will specify my stream manipulators. You can use the set precision manipulator to specify the number of decimal places to display in the output's numbers. The syntax of the set precision manipulator is as follows. The word set precision, followed by in parentheses the number of decimal places that you would like to display. In this case, I'll display 2. You can also format a program's numeric output with the set iOS flags manipulator, whose syntax is as follows. Set iOS flags, followed by a parentheses. Inside the parentheses, iOS stands for input-output stream, followed by 2 colons. At this point, I will specify fixed to indicate that I wish a fixed number of decimal points. I will then follow this with a pipe symbol, followed by iOS, once again double colons, and then show point. Parentheses closed, followed by a semicolon. Now this command will tell the C compiler to, at this point in the execution of the program, to set the precision to two decimal places, and then set the iOS flags to a fixed, and then to show the decimal point. So everything that happens from this point on will be in that format. Let's compile the program to see if we've written the correct syntax. As you can see, it has come back with 0 errors and 0 warnings. We'll now execute. The program is now running. I'll type in a 9. And as you can see, the square of the number is now displayed as 81.00, and the half of the number is 4.5. But notice 4.50, that is. Notice the number of decimal places are consistent now. You could enter different data for this set precision and set iOS flags to create a different effect for different situations. Just remember, however, that the effect of these string manipulators will remain in effect until you counteract them with a different statement. Also, one last reminder, you'll recall that in order to use these string manipulators, you need to have the compiler directive iomanip.h included at the top of your program. All the programs we've written so far have sent the output directly to the screen. Sometimes, however, you might want to print a program's output. You can print the output by first sending it to a file, then using C to open and print that file. To send a program's output to a file, you must include the fstream.h header file in your program. This header file contains the definition of the OF stream, which stands for output file. You can use the OF stream to create an object that represents an output file. We will modify this program to do so. I will first need to have an additional compiler directive underneath the ones that are already there. This will be include fstream.h. This will now allow us to create and send data to an output file. The statements that will actually create the output file can be placed virtually anywhere in the program as long as it happens before you're trying to send data to that output file. In this case, I will position the statements here, since from this point on is where I'm sending output either to the screen or to the output file. The key word is OF stream, which will give you access to an output file. The next word I'll type is entirely made up by you. I simply use outfile, spelled as you see it, followed by a semicolon. What this is doing is creating a file called outfile, which I will then be able to access through my program. The syntax of the open statement is the name of the file, which is outfile.open, followed by a left parentheses, and then in quotation marks include the name of an output file. Since the name of my demonstration program is Demo11, I will call this Demo11.dat to indicate that this data file goes with this program. Of course, this name is entirely made up by you and simply follows the rules that are established by your operating system. You enclose that in quotation marks and then enclose all of that in a parentheses, followed by a semicolon. This now gives you access to a file called outfile, which will be stored in a physical file called Demo11.dat. Now, if you wish, you can have the output sent directly to the screen, as it is now, or it could be directed to the output file, or it could be both. You can send it to both by leaving the cout statements that we have down here as they are, and send additional statements to the output file, Demo11.dat. At this point, I'm simply going to insert a line below the cout statement. Now I'm simply going to copy this line by using the copy and paste, so I have a duplicate copy of it immediately underneath of itself. And now I'm going to change this from a cout statement to an outfile statement. Remember, outfile with a capital F is what I called my output file in my OF stream declaration statement. So now this outfile statement will send this output to the screen, or excuse me, to the data file. At the same time, this output file gets sent to the screen. I'll do likewise for the other two cout statements. I'll simply copy and then paste. And then change the second version to an out file as opposed to cout. I'll do likewise for the third. Now, I have three statements that are being sent both to the screen with the cout statements, and those same statements will be sent to a data file, which can be retrieved at a later time, and can in fact be printed to a printer if that's what you desire. We'll compile the program and then execute. And the program runs as normal to the screen. I'll enter 7. As you can see, it does give us our output, and remember we've included now the iOS flags and the set precision statements to give us a uniform 2 decimal places. I return to the program, and now what you have not seen is that the output has been sent also to a data file. So I'll click on File and then Open, and I'll notice that in my folder that I have for my files, there is a demo 11, looks like a notepad type of file. In order to see this, you'll need to change this to all files. Otherwise, you're looking at only those CPP files. If I open this file, you'll notice that my output now has been sent to this data file, just like it did to my screen. If I wish to at this point, I could then send this to the printer by clicking File and then Print. To close this, you simply File and Close, and you're back to your program. So if you want to create output that is hard copy output, or is something of more permanent nature rather than going to the screen, you can use the fstream header file along with the out file statements to do so. Demo 11 is the sample program on your CD. Demo 12 is a demonstration program that will create a function and receive a string variable. The function will then display the output, and it also will send it to an output file. For this program, we will need 3 compiler directives: the iostream.h, the string.h, and the fstream.h. The iostream header gives us access to the cout and cin statements. The string header gives us access to the cin getLine function. And the fstream header will allow us to create and send data to the output file. This program is using a function that's called displayName. And as you can see from the function prototype, it will accept a maximum of 15 characters. The 16th character, you'll recall, is reserved for the null terminator. Inside the main function, the variable for the name is being declared with the appropriate size. It's being initialized to a null space. To accept the data from the user, we need the cout statement to prompt the user to enter their name, and then a cin getLine statement to accept those characters. Note the prompt says to enter a maximum of 15 characters, but the cin getLine statement will accept 16 characters, which of course is the null terminator. Then the function is being called by simply using the name, displayName, and then passing to it the name that has been entered by the user. Scrolling to the bottom of the page, we can see the function itself, which has the function header, displayName, and will accept a character variable, actually a string variable of 16 characters called name. The ofstream out file will allow this data to be sent to the output file, and the output file itself is called data12.dat. And then finally we have a cout statement that is going to send the output to the screen, and then an out file statement which will send the same output to the data file. I'll compile this program and then execute it. And as you can see, it is now prompting me for my name. I'll enter a name with a space to indicate or to demonstrate that the cin getLine statement will accept that blank space in between the first and last name. Pressing enter, it will then display what the name entered is. Press any key to return to the program, and now we should check to see if our output file actually did get sent to our data file. As you can see, there is a Data 12 data file. If I open that, you'll see that the name has been sent to the data file just as it did when it was sent to the screen. We can close this output file, or as you recall from the previous lesson, you can send this to the printer by choosing Print. I'll close this at this point. This program is called Demo 12 on your CD.